Hello. So right now I'm going to talk about deformations of rings. Here's our setup. So we're going to take A to be a square zero extension of another ring. So A prime to be a square zero extension of another ring A, and we're going to take a surjective map here, and we're going to. So by square zero extension, I'm going to have the kernel of this map be I, and I squared be equal to 0. Okay, we're going to take B to be a commutative ring over A. So it's going to be an A algebra. So let's say the commutative ring subscript A. And so I'm going to define smooth deformations of B to A prime, so an A prime algebra. So the objects here correspond to alpha B prime, okay, where B prime here is an A algebra, an A prime algebra, with an isomorphism like so. So of B prime. So when I base change to A, right, it's going to be isomorphic to B. Okay, so this thing could be thought of as B prime modulo IB, given a certain exact sequence. You can watch the video on deformations, or what is a deformation of a scheme, and I talk about this a little bit. Okay, so sometimes I'm going to call this J. Okay, so a morphism of these pairs, so if I have two of them, okay, I need to define what this is. Well, it's just going to be a morphism of rings here, okay, where with the following property. So I'm just going to take this morphism of rings, B2, here, and here this is F, and then I'm going to base change to A. Okay, tensor, so this is a functor, so I can do this. And now I'm going to take the identification here, alpha 1. And this is an isomorphism by definition. This is part of the data. This is the other isomorphism here. And for this to be a morphism of deformations, I'm going to require, the requirement is that, well, if I follow this around, so I take alpha 1 inverse, so this is an isomorphism. This is a map here. So then I'm going to take F tensor A prime over A. And then I'm going to apply alpha 2, so that this thing is going to be equal to the identity of B on the nose. So this is just the identity here. Okay, so this defines the category of deformations. I wanted to make a remark about what automorphisms are. Automorphisms of deformations. So this is just going to be a map. So if I take one of these B primes like this, such that sigma B prime is just going to be congruent to B prime mod IB. And again, this is what I was going to call J sometimes. So it's just the identity, a lift of the identity map. Okay, so it does nothing to after reducing mod J. Okay, now the point of this video is to prove the following lemma. Well, I need to give you the setup. So here I'm going to take B to be an A algebra. I'm going to take A prime to be a square zero extension of A. with this exact sequence of A prime modules. So this is the kernel of the map. And the two things that I want to prove are the following. So the first thing I want to prove is that for every two deformations are smooth deformations are going to be isomorphic as deformations. So there exists a sigma B2 prime. Okay, the second thing that I want to say is that I'm going to fix some deformation. If I fix some deformation, I want to describe the automorphisms of the deformations. So the deformations to okay, so I fix one of these, and so what I want to say is okay. So I'm going to say that I make an identification. So identify B prime mod I B prime, and let's say this is equal to B. Okay, so J is equal to I B prime. Okay, then the deformation automorphisms of B prime with respect to B is just going to be equal to the derivations from B to J. Okay, so there's a small remark here to make this make sense, is that J is a B module, and this follows from the fact that J squared is equal to 0. Okay, and the natural B, so the natural B prime module structure on J, so it's a subring of a submodule of J structure on J, factors through the map B prime to B. Okay, so so that's all it's saying, is that there's, yeah, so this is the, I don't need to say any more about that. Okay. All right. Okay, so let's prove the first part. Okay, so the first part, so proof that any two deformations are isomorphic as deformations. So this is in the case of rings. Okay, so here what we're going to do is we're going to look at the diagrams that we have. Okay, so I claim that so let B1 prime and B2 prime be two deformations. Formations of B C ring A to A prime algebras. Okay, so here we have, so let's take B1. Okay, so this has a surjective map here, and B2 also has a surjective map here. They're also both A algebras. Okay, and notice here that this thing here is a square zero extension. So here, B is isomorphic via, say, alpha 2. So given the deformation data, then this is isomorphic to B2 prime mod J, where, let's say J2, where J2 squared is equal to 0. Okay, now, since I am looking to smooth deformations, there exists a map here from one of the deformations to the other one. So this is by the infinitesimal criteria of smoothness. So there exists a map sigma. So sigma, there exists a map sigma from B1 to B2 by infinitesimal lifting property. And I think that thing, the infinitesimal lifting property written down like this, was originally written, I think, by Seidenberg and used successfully to a great extent by Grothendieck and a lot of other people. Okay, so that's that. So we have this map. Now we need to show that this map is an isomorphism. Okay, so we're going to consider the sequence. And I consider the sequence, again, in the deformations video at the end of it. So you can go look at this again. So we consider the sequence of A prime modules here. So this is an exact sequence. So since we assume that this map is flat here, or sorry, it's smooth, it's also going to be flat. So flatness tells us that 0 I tensor A bi prime, and this is so A prime, so tensor A bi prime to, and then we have A tensor A prime bi prime, so A prime A prime. Okay, so we have this new exact sequence for both of these guys. Okay, so this thing here is just isomorphic to IB prime, and by alpha I, we know that this guy is so these cancel. So this is canonically isomorphic to BI prime. This guy is canonically isomorphic. Well, not canonically. The part of the deformation data is that we have an isomorphism to B. Okay, so we have both of these things. One thing I want to observe is that this here, so this is what we called maybe JI. So this guy here, the claim that I want to make real quick, it's a very quick thing, is that I tensor A prime over BI prime, this is going to be isomorphic to I tensor A over B. Okay, the proof of this is really quick. So the proof of this says that, okay, so take K to be an element of I, and take B prime to be an element of BI. Here we can just consider K tensor B over A prime of B prime minus K tensor let's say B prime plus, and then we'll add some I. So we'll say I is also an element in here. Okay, this just breaks up. Let's say that this is K tensor A prime B prime minus K tensor B prime minus K tensor I. Okay, these are 0, and then this is equal to, well, this gets to move over since we're tensoring over A prime. So this is just minus Ki tensor A prime, and then this is 1. And so now this is equal to 0 since I squared is equal to 0, since we took a square 0 extension. So this uses the square 0 extension property. Okay, so this is what we have. Now I'm going to show that the two BIs are isomorphic. Okay, so we're going to have that the two BIs are isomorphic. Both of these turn out to be, okay, so let's look at the two sequences. So down here. So we have the two sequences. We have the two sequences are I tensor A prime BI prime to BI prime to here we're going to have B into 0. Okay, and so sorry, let's do 1, 1. Okay, and then we have 0 I tensor A prime B2 prime B2 prime B0. Okay, and here, by the claim, these two things are just isomorphic to this. So these two are isomorphic, and these are both just I tensor A over B. These are also isomorphic. They're equal, but we're using these isomorphisms here. Okay, and okay, this is equal, this is equal. So we have a sequence like this where we have 4 isomorphisms, and by the 5 lemma, this is an isomorphism. So we get this map sigma. Okay, this proves that any two extensions are going to be isomorphic. There's maybe some details to check that it's an isomorphism of extensions, but I'll let you guys do that. All right, now we're going to prove the second part. We're going to prove that the automorphisms of these deformations correspond to derivations. Okay, so what are we going to do? We're going to fix B prime, a deformation of B, which is an A algebra, okay, to A prime, and then we're going to fix sigma from B prime to B prime in automorphism. Okay, and then what we're going to define is define theta to be equal to sigma of B minus B. Okay, so first of all, we're going to make a little claim here. The first claim is that theta is a derivation from B prime into J. Okay, so the proof of this, first we need to observe that by the definition of an automorphism of deformations, sigma B is going to be congruent to B mod J. Okay, that's just what we had, and then what we're going to do is we're just going to write out what you do to show in calculus something's a derivative, essentially. So B1 sigma B2 minus B1 B2. So this breaks up. And then we can introduce a factor, B1 sigma B2. So this is going to be just this cross factor. So sigma B1 B2 minus sigma B1 B2 minus B1 B2. And now we factor B1 and sigma B2 minus B2 minus, so now we're going to have a minus here, and we have sigma B1 minus B1 B2. So this is sigma B1, and we have theta B2 minus, this is, minus minus. So am I missing a minus here? 1 second. So sigma, this should be a plus overall. So I want this to be plus theta of B1 B2. Let's see here. So I introduce, so I have to do this plus here. Okay, so these have to cancel. Okay, so this is what we have. Now this becomes a plus, and now we're okay. Here, this becomes, so now here's the thing. So now this is the thing where I said about the module structure, J, so the multiplication onto something. So first of all, you can see that the difference here, theta, this is going to be inside J, since these are both congruent mod J. Okay, so this is going to be an element of J, and multiplication by something in B prime is only defined modulo J. So we can replace this to B1 since these things are congruent mod J. And this gives us the derivation property, B2. Okay, so that's what we have. That's not bad. Now I want to do the part. Now I need to conclude that this can actually be a derivation from B to J. Okay, so first of all, observe that if we have a derivation from B prime to J, okay, this of course corresponds to so this is isomorphic to even so a map morphisms of B modules or B prime modules from omega B prime to J. So really we have some map from omega, so maybe I can write it like this, some omega B prime to J. Okay, now we observe that J, as I said, as I used over here, this is really a B module. Right? I mean, the B prime module structure factors through the natural B module structure it has from the square zero property. Okay, so since it's a B module, we might as well tensor up to B here. So we can tensor up to B over B prime with omega B prime here. And this factors is so, and I claim that this is isomorphic to B, omega 1 of B. So we really have maps from of B modules from omega 1 of B to J. Okay, and so using the fact that homomorphisms of B modules from omega 1 of B to J is really derivations from B to J as B modules, this concludes what we want. Provided we show that essentially, okay, so this gives you the idea of the construction, and we'll omit the part that this induces a torsor on the set of that there's a bijection between these. All right, so that's all I'm going to do for this. Thank you for watching.